to go? I guess you're as ready as I am. Just let's take the last few seconds before we start out. Yeah. Now the time has passed 1400 here on my watch at least. So first of all, let me present myself. I'm Jens and I work for Danfoss Cooling. This is the absolute basic I'm going to tell you about evaporative cooling. So it's for you who are beginning to learn about cooling. If you have been working with cooling, whether it's HVAC or it's refrigeration or something else, then this just might be a good opportunity to catch up on a few things, but it will be for the absolute beginners. So let's have a look at the agenda first. Let me share my screen. Here we go. And I'll just hide that one. So again, this is what it's about. And first of all, I'll just give you a presentation of myself very briefly, and then we're going to talk about why cooling in the first place. And what is phase change? Energy. What does energy have to do with anything? And the entire process of cooling, of course. And finally, we will end up with the fridge, which is an animation that you just might have seen. If not, then it's absolutely fine. Now, I'm Jens Andersen, and I work for Danfoss Cooling, as I said before. I'm titled Application Development Specialist in the Department of Concepts and Content. I'm an electronic engineer and teacher. I've been working for Danfoss for 40 years now, of which 20 plus at Danfoss Cooling. I've been doing all kinds of funny stuff, podcasts, and other fun stuff, and worked with digital communication for at least 25 years now. So why cooling in the first place? Well, we humans like to be in control of things. One of the things that we like to control is temperature, and it's pretty easy to heat up things. You just light it and eventually you get hot. But cooling is a different matter. It's a bit more tricky. And no, we're not talking about the process. We're talking about the process of cooling, not just, like you would do tomorrow or this afternoon, go out, put your Coke in the fridge and then wait till it's the right temperature for you. No. We're talking about the process of cooling. So cooling down or even freezing stuff is a great way of keeping the food fresh, and that is one of the primary reasons for cooling. The top right photo is, you can see it over here, is actually taken from one of the local restaurants where you can see the compressors for some of 8 different cooling facilities. It could be a cold room, or behind that, if you look at the picture, you can see the door to the cold room, and behind that, if you could walk into the cold room, behind that you have a freezing room also. Again, all for food stuff. But keeping ourselves cool is another reason. Oh, sorry. Also, data storage facilities need cooling, and industrial machinery of all kinds could need what we could call active cooling, or heating for that matter. A small detail in the urban rigger project by it's an architect company in Copenhagen, is the utilization of the sea and food water energy to heat the accommodations. You see them over here to the bottom right. Yeah. So keeping ourselves cool is also another thing that we, are working with. We might live in an area where air conditioning is a necessity. Or maybe just a convenient way of obtaining a nice living environment. So you need an HVAC system. HVAC stands for heating, ventilation, and air conditioning. And it's another example of where cooling plays a major role. You may know from your domestic HVAC system, or maybe from your heat pump, again, depending on where you live. A large central air conditioning system in stores, hospitals, hotels, and residential buildings. It could be equipped with what we call rooftops, or it could be chiller systems and places where evaporative cooling comes into play. It's also about making your life comfortable, either by heating your living rooms up or cooling them down. But also, the control of humidity is done by means of cooling the air, and hereby condensing the moisture in the air, so that the HVAC system serves several purposes. So how do we actually cool things in the wider sense? What mechanisms is in play? Well, it's basically down to the laws of nature, or rather the utilization of the laws of nature. And this is what I'll spend the next 20 minutes or so on, the wonder of nature, and maybe also a small, maybe in this context, small but significant scale. I'll be using water as an example of evaporation and condensation, but that's only because water is something we all can relate to, and we all know H2O and how it behaves in nature. I can see there are some questions pouring in here, and I will answer some of the questions later when we get there. I can also see that there are some rather high-level questions, if you like, so be aware that this is the absolute basic of refrigeration we're talking about here. But let me come back to the questions afterwards. Just we'll continue for a few more moments now. In reality, though, when we're talking about cooling, it'll be all kinds of different substances that we will be using. It could be some synthetic or chemical brews, or it could be what we call natural refrigerants, like butane, methane, or CO2 for that matter. But let's first focus on what water can teach us. The first thing we need to sort of accept and digest is the three phases of water, or rather H2O. If H2O is frozen or in its solid phase, yeah, well, we do have a name, and I'm sure you know that, of course, ice, right? And if it's in liquid form, it's, of course, water. And if it's in gaseous phase, we call it steam. Nothing new there, no. But it's the same substance, regardless in what phase it is. It's just H2O under a different phase. Actually, we're pretty good at giving names to things related to water. The phase change of H2O are when the substance goes from one form to another, like from solid to liquid, or if it goes from liquid to vapor. Also here, we have other words for the same thing. Ice thaws, water boils. Nothing new again. Thawing and boiling is each their own phase change from one phase to another. We just use other words. And this is actually valid for all substances. It's just that we think of them in a different way. Take CO2, for instance, or carbon dioxide. We think of it as something gaseous, but it also has a solid form or phase. Then we just call it dry ice. It's used for keeping things frozen for a shorter period, like when you take a bag of frozen peas home from your supermarket. They may offer you a free pack of dry ice, depending on where you live again. Just as a curiosity, you can see also iron, or Fe for ferron, has a melting point also at 1,538 degrees Celsius. and a boiling point actually on 2,862 degrees Celsius. So also that type of solid matter or substance has 3 phases. We just don't think of it, usually at least. Likewise, also so-called natural gas, which usually is gas, but it's kept in liquid for transportation and in huge pressurized tanks on ships, for instance. But actually, it's the phase change itself which is interesting. That is, when a substance goes from liquid to vapor, for instance, or from vapor to liquid, both ways. Because, and this is where it starts to get interesting, because in the process, some pretty strange things are happening. And if we zoom in all the way down to the molecular level of H2O, you'll see, if I can get this rolling, you'll see molecules very neatly ordered. They're shivering slightly. And I'll just stop for a moment. The shivering of the molecules is an expression of the internal energy, the energy that the molecules themselves holds on, so to speak. They possess an energy already, and that shivering is actually an expression of that. We'll keep adding energy to this substance, and you'll see the shivering starts to get a bit more intense. And the funny thing is that it'll actually also, you'll see the neat structure will break up eventually. And this is where the ice has thawed. It's no longer neatly ordered, as you can see in the start. I have just started it up again from the beginning, and we are adding energy to it, and you can see the shivering is getting more intense and the structure is breaking up. And this is actually where the ice has thawed into liquid. I'll just let it run a few seconds more. Yeah, and here we go. Oops, yeah, thought so. Let's see if I can start. We are here, I think it was. Yeah, let's just pause here. You can see there is no structure anymore. This is the liquid form of H2O. Now, if I can make it run again, yes, you'll see what happens now. It looks as if it's exploding, and that is not the reality. This is not what will happen. Damn it! In real life, what will happen is when it boils, and this is the expression of the boiling, is that the molecule structure will actually open up, so to speak. It'll demand more space for the molecules to work in. Yeah. And finally, we can go to the next slide. I'm sorry about this. Energy can take many forms. And of course, you know all about electrical energy from batteries. I'm sure you do. Or the plug in the wall, but also kinetic energy or motional energy. That's the energy you have in an object in motion, like a tennis ball, for instance. Also, chemical energy, where you have energy stored in a liquid kerosene, for instance, the lamp boiled, where the chemical energy is set free when you set it on light. And these are only a few of the examples of energy. But the one that we should talk a bit more about is thermal energy. And but I guess we should just take a look at what energy is measured in or measured by, and it's called joule. That's the SI unit, or joule, I guess you pronounce it. But you'll also see it, depending on where you are, you'll also see it in kilowatt hours, in calories, in British thermal units, that's the BTU, and whatever else. There's a lot of different units that is being used for energy. Energy can also be stored in many different ways. Some are better than others. Maybe electrical energy in batteries or accumulators, whereas storing heat is maybe not exactly the best way. But for a while, you can store energy in the form of heat. I mean, you may still burn your fingers on a hot stove, sorry, even as it has been turned off. Yeah, I'm sure you know that. Energy in the form of heat will result in you moving your hand quite fast. And energy in the form of heat is what we will be talking about the next few moments. Now, let's just cement the fact that heat equals energy. And as a proof, we'll boil an egg. You heat up the water. And the strange thing is that you heat up the water, and obviously it gets warmer and warmer, etc., but only to a certain point, or rather only to a certain temperature. The temperature turns out to be pretty much 100 degrees Celsius or 212 degrees Fahrenheit, which happens to be the boiling point of water. Let's see if I'm lucky this time and be able to stop and start the animation. That's the energy you apply to the boiling water, but the temperature will not get any warmer as long as it boils. You could say the boiling process is stuck on 100 degrees Celsius while the water evaporates. All additional added energy is now used only for changing phase from liquid to vapor. You could pour any amount of energy into the water. It'll not raise the temperature, it'll just evaporate. I can see one of the questions being asked here is actually about this, and I'll come back to that later when I start answering questions. Now, if we look at the lid, let's see if I can be lucky and start it again. If we look at the lid itself, which is colder than the pot itself, you can maybe see the droplets are forming, and that's the water condensing. Condensing is another very important part of cooling. That is where we get rid of the energy that we picked up while boiling. And you can say the condensing is a complete opposite of the boiling. So we could, in fact, let's see if I can get to the next one. Here we go. We could, in fact, form a circuit with two phase changes from liquid to vapor and another from vapor to liquid. And actually, if you look at the drawing, we could have the water from lid dropping into the pot, and we would have a complete circuit. But let's first again have a look at the first animation again, the one with the H2O molecules. And pardon me for repeating this again, but it's actually quite important. The slight shivering of the molecules is a potential energy in the form of heat. I just said that before. At this moment, the ice of water is frozen, and you will see the molecular means orderly organized module, as I told you that before. And you can now see that the heating of the ice cube is happening. The shivering gets slowly more intense, and the temperature rises from -20 maybe up to 0 degrees. Now the temperature has reached about 0 now, and you can see it melts. And we keep adding energy to it, and here you have this, which looks like an explosion, and that's not the case. It just boils. But the water or the boiling H2O is actually demanding more energy. And this demand of more space, not energy, space, is actually so powerful that it can run a train. You know it from a steam engine, for instance. Yeah, let's see if we can move on. But boiling is not just boiling. And this is where it starts to get really funny. Because if we're still talking about water, we have been working at sea level, or rather, you can see it here, the atmospheric pressure at 1 bar or 1 atmosphere. That would be at sea level. So water boils at 100 degrees at sea level. But if you go up in the height where the pressure is lower, then the boiling temperature will be lower. Or if you took a trip down some of the deep mines in South Africa, you'd see the water boil at a higher temperature. I don't think you can get down to 500 meters, sorry, 5,000 meters, but at least some 4,000 meters, I think it is. But still, it is a higher pressure temperature the water boils with, because you have a higher pressure there. And if you look at the curve, let's have a look at the curve here. You can see this is atmospheric pressure, and if you lower the pressure down to something like 0.025 bar or 25 millibar, the water will boil at 20 degrees Celsius. That's worth knowing, actually. Now, so far we've been working or talking about water, but what if we could find something which would boil at atmospheric pressure somehow? And that is actually the case with something called butane or isobutane. It boils at minus 12 degrees Celsius at 1 bar. So that would actually mean that we could construct a closed circuit with isobutane inside, where we install a pump in the form of a compressor. And that's also pretty important. This is a compressor, it's not just a pump. And you'll see why in a few seconds, if I can get this running again. Here we go. You can see the piston goes up and down, and it actually does suck pressure out of the low side here. It sucks pressure. You can see the pressure just lowered here. And there are valves up here. There are 2 valves. One is the suction valve, and the other is the condensing valve, or discharge valve it's called. Now, let's just have it running a few seconds more. You can see it sucks, and damn it, sorry. Keeps messing with this. Let's go here to when the isobutane is actually boiling, it demands, it will have energy to be able to boil. And this is what it does now inside the fridge. Is actually, it steals, you could say, or at least that's what I call it. It steals energy from what is inside the fridge, like the milk or whatever, cheese maybe, and then it transports the heat, so to speak, into the vapor, the boiling of the isobutane. Yeah, let's see if we can get it running. Yeah, here we go. I'm still lucky. And you can see it's being pushed over to the high pressure side. So we have a low pressure here, and the piston is actually pressing the vapor over into the high pressure side. And let's see if I'm okay again. And here the gas is actually cooled down, and when it cools, it condensates. So the vapor is actually turning back to being liquid again. And that's also what you can see is being collected at the bottom here. And finally, let's see how it works. You can see the liquid refrigerant, that is the isobutane in this case, is actually pushed back into the evaporator, where the gas is actually evaporating. Yes. So it's all about pressure. And that is actually where the trick, you would say, with refrigeration is that we are controlling the pressure. It would be not correct to say that we're not controlling the temperature, but because we are controlling the temperature. But you could say we are controlling the temperature by controlling the pressure. Grant. So let's just have a look at the ordinary domestic freezer. Again, if I can get these animation running, I hope I can. So let's start from the beginning. There are reasons why we cool stuff here, food stuff, to keep it fresh, to keep it as long as we can. Of course, it's still it's getting better over time, but that happens and slower in a refrigerator. What we do is we pump refrigerants like isobutane. It could be anything else, but let's just talk about isobutane a bit more. Around in a closed circuit, high pressure parts, and where the heat is dissipated on the backside of the freezer. I'm sure you know that. It's the part that collects all the dust. I'm sure you have seen that. And remember, heat is energy. So inside the fridge, the pressure is low. So the evaporating refrigerant is stealing, it's taking energy out of the surroundings, here the foodstuff. And the compressor pumps the heat and pressurized refrigerant back to the rear of the fridge, where it dissipates the heat or energy it just stole from whatever is in the fridge, if it's milk or if it's something else. And on the back side again, the refrigerant cools down, it condensates, and it returns to the liquid state and is pushed back into the low pressure area, the evaporator. Yeah. Yeah, and that's basically it. It's an ever ongoing circuit. Yeah, that's it. And that's basically what we do at Danfoss, or at least the Danfoss Cooling department. We are making all kinds of different controlling parts of big or small cooling systems, refrigerations, HVAC systems, whatever else. You can see one of my colleagues, Lasse here, he's looking at 600 kilowatt something chiller that is actually cooling 40 meter. That's 10 stories building, with some of the more innovative engines. You can see the top green ones there. That's oil-free compressors. They work with magnetic bearings, so oil is not needed. But all this is for later lessons. So yeah, you can sign up for some of our lessons later. But let me just have a look at the questions, and hope that you have enjoyed this very quick and very sort of condensed trip through some of the laws of nature, with phase changes and evaporation, etc., etc. So what I'll do now is I'll just have a quick look at some of the questions you've sent me and see if there is anything I can answer right away. There is someone, what is superheat? That's a good one. Superheat is when the vapor, after it has been evaporated, of course, then you have the vapor. When that is heated above the evaporating temperature, let's say the refrigerant has completely evaporated at 10 degrees Celsius, but you keep heating the refrigerant up to 15 degrees Celsius. Then the 5 degrees from the 5 degrees from the 10 degree to the 15 degree would be your superheat. Usually you would measure that in Kelvin, but the happy thing about Kelvin and degrees Celsius is that the difference is 1, basically. 1 Kelvin is 1 degree Celsius. Let's see if there were yeah. The discharge line temperature in an air-cooled and water-cooled system, how can we control and troubleshoot that? Yeah, that depends exactly on how it is cooled. That is the condenser. You can have an air-cooled condenser, and you can have a water-cooled condenser, and you might actually have something else as well, which I don't know of. But that depends quite heavily on what type of condenser you have. So I'm not able to answer that question directly. 407C refrigerant, yeah, that's a great one. If we take that out, refrigerant from liquid line and measure that rate, oh geez, yeah. That is a fantastic good question. That's the mixture of different refrigerants, but honestly, this is not for today. This is for a bit more advanced levels, so to speak, of refrigeration. Yeah, when is the receiver needed for chillers or the refrigerant slider? Yeah, that is when it's actually more or less used everywhere. Let's just have a look at if I can get this running again. Just hold on a second. Yeah. See, if we have this very, very, very simple circuit, you would have your receiver sitting somewhere in between the condenser and the evaporator. And it would be sitting in front or before the metering device or the expansion device. So it would sit somewhere here or there. And if you look at, if you take an ordinary fridge, you'll actually see that there is a tiny little receiver sitting just in front of the expansion device, and it would always be in front of the expansion device, where you of course have the liquid part of it. And then you're asking about how to connect different sensors. Again, I think this is also for a different class or different webcast. Yeah, that's correct. There are some nice videos on superheat and what superheat is and how to control it, etc., and what it implies in general. Again, the question about sensors, I think we should leave that out for now. There's a question, how to know if the compressor is turning the right way? That's a good one, actually. And the simple answer is, it depends on what type of compressor it is. What you have here, the one that we're showing here, is a reciprocating compressor. And you might be able to tell that even if the piston is, or rather the motor is turning the other way around, the piston is actually doing the same thing. So in principle, on a reciprocating compressor, if it turns one way or the other, that doesn't matter. The flow of refrigerant doesn't care. That is the valves taking care of that, and the piston. The piston just jumps up and down, and will do so regardless what way the motor is turning. So it doesn't matter. But, and there's a big but here, and that is if it's a scroll compressor, for instance, then the rotation direction has an extremely important significance. But you will be able to see that quite easily. If the compressor is turning the wrong way, the scroll compressor is turning the wrong way, then you won't have little or any compression at all. So that is fairly easy to see. So I think that should be answer enough. But it also implies actually that we have several different types of compressors in the market, and I've just mentioned two. Receiver in the cycle, yeah, no, that's a good question. Yes and no. Actually, you have a receiver also in the liquid line itself, but now we're talking about small, very small systems. In larger systems, yes, you will need a receiver, definitely, to be able to have a higher dynamic, so to speak, so that the system can work under more different loads. And there's a question about what would flash gas be. Yeah, that's another good one. Imagine that somebody is actually, if you look at this circuit again, if you take and you take a hammer, to be very, 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 you shouldn't do that. Please don't. But if someone is actually jumping up and down on this line here, and it crumbles down, and you get a narrowing of the liquid line, and that's important. On the liquid line, you have a narrowing. Then you will have a possibility, or a risk rather, to have a pressure drop from one side of that narrowing to the other. And that narrowing will lead to what we call flash gas. That is, that the pressure will actually make some of the liquid evaporate, which means that it will turn into gas. Yeah. Refrigerant boils at an atmospheric temperature. Is it different? Yeah, that depends on which refrigerant we're talking about. Some refrigerants might actually boil at atmospheric temperature. You can use, for instance, our fantastic app, the refrigerant slider, to find refrigerant that actually boils at one bar absolute or 0 bar gauge. Try it out and you'll see it. Have you some good book recommendations? Not right at hand, but there are quite a few, I can tell you. There are a lot of different books out there, and I would simply just have a look at Amazon or wherever you are using to buy your books. Yeah, correct, Jose. That is actually a bit funny, because you're actually touching on steam engines as well, and but it's the same rules, you could say, apply whether we're talking about refrigeration or steam engines, for that matter, even though it's something completely different. Is pressure related to temperature? Oh yeah, indeed. Also, in theory, yes, absolutely. I think we should keep it at a lower level, but you could let me just have a very tiny little remark here when we're talking about pressure and temperature. The higher pressure, the higher temperature will, or the higher pressure, the higher the boiling temperature will be. I'll repeat that again. The higher the pressure, the higher the boiling temperature, and vice versa. The lower the pressure, the lower the boiling temperature. Yes, and that's good, Lasse. Lasse is the guy who's sitting behind the screens and adding comments to the chat. And yes, there are a lot of different e-lessons spanning from this level, which is the absolute starter level, so to speak, and up to, say, the more advanced level of the compressors I just showed you before. But if that is all, then there's a question coming in here. Can we find out how many kilos gas there is in a cylinder if we know its pressure, temperature, volume, and so? The immediate answer would be yes, but I'm not absolutely sure I understand the question in itself. But let me look at the subcooling, please. Yeah, subcooling. Just hold on a second. I'll show you again. Let's go back to this one. There we go. Let me just, the subcooling. I think I told you, I hope I told you, no, I know I told you that when the vapor has cooled down, it gets liquid. Now, the liquid here could have a long way to go. It could also be that it's still, some of the liquid would be inside the condenser. Then the liquid itself would also be cooled down, so that the liquid temperature will be below the condensing temperature. And again, just like the superheat, the subcooling will be the temperature difference from the, you could say, the condensing temperature to the liquid temperature. And the importance of subcooling is that the lower the temperature of the liquid is, the better you actually are capable of utilizing the evaporative mechanism, so to speak. Not that you could cool it down to minus something. No. There are limits, of course, but it's always a good idea to have at least some 10 to 15 Kelvin subcooling. Depending, again, of course, on system and what the requirements are, etc., etc. So subcooling is very, very, very basically is the additional cooling of the liquid refrigerant. Yes, and Lasse, you are supplying me greatly there. Thank you, Jose. Yes. Yeah, but then I'll just say thank you for today, and hope that you will be back another time. Not sure when or where, but you can thank you, Lasse. You can actually listen a bit more to some of the fantastic things I have to tell you about cooling by listening to some of the podcasts that we are distributing. They're called Chilling with Jens, and you'll find links to the podcast on our homepage. Sorry. There was another question here, the evaporator manufacturer size in liters. I'll not come into that now. Take that at, say, a higher level in instructions. Yeah, we have, can I share that, Lasse? The Chilling with Jens link. I'll read it aloud. It's Chilling with Jens, in one word, .captivate.fm. That's where you'll find the podcasts. Oh, can I do that? No, apparently not. Would have been nice though. But thank you so much for today, and I hope you enjoyed it. And maybe we'll see or hear each other some other day. Thank you.